Well, Sam, we're getting there. Our waveguide's almost built. We have two kinds of waves, TE and TM. We saw last time how to get this equation, and now we have to solve it.
The beautiful equation, Helmholtz equation.
Helmholtz equation and the symmetry, they're the same. Of course, the grad perpendicular has the x and y derivatives, so we need to do something about the plane of the waveguide, what the fields are doing, and we know that the energy is moving in z. So let's focus on TE.
Yeah, let's try it. Let's try it. Okay. Well, I guess we have this written out already.
Yeah, we have it already. So that's the wave part, and this is the thing we don't know.
Oh, okay. Okay. I guess because. Well, Hz doesn't only exist in one location on the waveguide. It exists on the entire xy plane. So we want to know what Hz is across the entire waveguide. Is that what it is?
That's right. And what we do know is we know that the tangential electric fields vanish. That's going to give us a constraint. But we have to kind of guess what that's going to be.
Oh, okay. Yeah. Any hints?
Yeah. Why don't we use this as a hint?
Okay.
Let's look at what happens when we try to get a standing wave on this slinky. So we'll start trying to get one pulse and then two. So there's our fundamental mode.
So it's a standing wave.
It's
just
a
like
standing wave, just like we've been talking about. So it's only got one peak and two nodes. There you're holding them. Now let's go a little faster and see if we can get. So that's almost three, right? We have two peaks and a trough, so that's three. If we slow it down, let's see if we can get two. There, there. There's two. Almost.
Kind of two. It's
kind of two, between 2 and 3. We still got a lower peak.
So
anyway,
you get roughly two antinodes and one. Two
anti-positive nodes and one negative, so third mode. We actually got the third mode. If we eliminate the bottom one, we'd get just two, but we've got 1 and 3. So now...
So do you also get different modes in the waveguide?
Well, we will. So let's write this down.
Hey, the board finished it for me.
Wow, that's fantastic.
Good board, good board.
How did you get that?
How did the board get that?
How did the board get that?
Let's ask the board, how did you get that?
I don't know. Sam, you tell me.
Okay, well, there's a multiplication of these cos and sines, and I don't see a traveling component in here because the traveling component is out here. So I figured this is a standing wave pattern.
Yeah, it's a standing wave bouncing between the two walls in X and in Y.
Okay.
And we did this before, and we did a simple transmission line. When we had a shorter and open, we got a e to the plus something and e to the minus something added up to get cosine. And this is a shifted version of that.
Okay.
So that's a general situation. And now we got to find kx and ky. Wow. And then we're finished. We have the complete description. Hard to believe, but it's true. So we just got to do the last piece. Find the constants, find kx and ky.
Wow, that's been a wild ride.
It's a very wild ride. Well, let's see how it goes from here. Well, Sam, we're on our way. You got f of x and y. We just need to know these constants, kx, ky, and the coefficients in front.
I guess the way we find them is through boundary conditions?
Boundary conditions on the sidewalls. X equals 0, x equals a. Tangential E must vanish. E's in the...
Yes, because E comes in to a perfect conductor, and then it just get annihilated.
That's right.
An opposite E field at the conductor.
As we know.
As
so
we know.
EY is 0. So we have to differentiate this and put E to be 0 because we know that it vanishes. So at x equals 0, when we differentiate this, we find that this becomes a cosine, and at x equals 0, that means B must vanish.
Must be 0, yes.
At x equals a, we're going to differentiate this, and it becomes minus kx, a cosine, and so on, sine rather, And so we have this condition. There's a kx here, but it's a constant. So we have this equals 0. Now, two possibilities. A is 0, then everything is 0. So we can't have that. But we have sine kxa is 0, and that fixes kx.
Okay, sounds good.
Kx is equal to m pi over a, because it's a multiple of pi after dividing by a. So it could be 0, 1, 2, 3. It's not 0 again, because that's not very interesting.
Okay.
So the first m that works is pi over a.
So, well, you're telling me that each integer m gives you a condition that satisfies this equation.
That's the
So,
mode.
That's the mode.
We did that with the slinkies. We
Yeah.
got m equals 1 and m is equal to 3.
Beautiful.
So what's next?
Well, I guess we've gotten kx. We don't know what ky is yet.
Can you guess?
Hmm.